Okay, so today's topic, fracture. And actually I'm mainly talking about real-time fracture simulation because it's a lot of fun to tear things apart in real time. And 'cause originally I was planning a fully physically based fracture technique, but since I saw some of the groups are submitting their final project proposal using some real-time fracture technique using Voronoi diagrams, so I changed the topic a little bit to mainly talk about real-time dynamic fracture. Okay, so but still I want to cover really the basis of how people are going to simulate fracture. The first one, the original topic that I was prepared, the physically based fracture. So in last two classes, we know that we can discretize a mesh into lots of finite elements. So let me triangulate this. You can triangulate or tessellate any of the mesh using your favorite technique. And since there's a lot of elements in it, once I have an impact, say over here, I can first assume I know find the impact location. All right, assume there's an impact over here on that element, and then we can deform the entire mesh a little bit because we know everything is deformable in the real world. The only difference is some of them can deform in a really large way, but some of them can only deform a little bit. And after the little bit deformation, using the technique that we talked about on last week, we can find the stress and the strain on all the elements. All right, because they have been deformed a little bit, their deformation gradient are no longer identities. We can find the strain, stress over all elements, and we can find those elements with really large stress, larger than the threshold that should set, and if the stress is larger than some threshold, you're gonna break it. So here, the example is pretty simple. It's straightforward. If we have an impact over here, we can find probably the strain over this element may be really strong, over this one maybe a little bit strong, and the strain on the rest of the mesh is fine, just fine. So we're going to just break this part of this mesh and just use and make them to be fractures. Okay, and this technique is actually really old and classical way. You can backtrack it into 1988. And there's also lots of details, such as you also want to group some of the elements together because you don't really want to break it into single elements, and those things are too small to display on the screen. And also, if you are tearing an object, you want to also maintain the line of where you're tearing to make it a continuous line instead of breaking it in a random way. So there's also lots of details in this simulation, but I'm not going to talk about it right now. All right. Also, one thing is this fracture scheme is also dependent on the resolution of the mesh. So if you have really large elements, probably you're not going to do it. And also, even if you have really small meshes, the line that you are breaking is always the line of the border line of the elements or the faces if it's a 3D tetrahedron, right? So you can always expecting those kind of a zigzag line when you're tearing things apart. If you want to get a really clean cut, probably you cannot do it. Okay, and also there are little, advanced method based on the physically based fracture scheme, which is using splitting elements. So instead of saying an element is the smallest thing in our simulation, we can even split one element into halves to make the fracture happen. So if I still have a triangulation over here, and I have an impact here. Okay, so if I have a really strong stress on some of the elements, I can also split it on the strongest impact force direction. There and to there, to something like this. So you can have sort of a smoother cut because you're splitting the element. This method is firstly come up with by Professor James O'Brien and Jessica Hawkins in 1999, and but there's still drawbacks because each element can be split only once, and still it depends on the resolution of the mesh a lot. All right. So if you're really interested in those purely physically based fracture, you can just go back and to see CZR papers about it. Okay, and there's so under a spectrum of a fully automated one, like this physically based fracture, and there is also like a fully controllable one if you want to prefactorize something by some artist and run it in runtime in a real fast way. Okay, so those method is always called a prefactorize or it's a prefactored simulation. So the first thing is instead of working on all the triangles on all the elements, most of the techniques are working on polygons directly. Think about it. Think about a hexagon. If I have a hexagon, you can triangulize it using Delaunay triangulation or your favorite triangulation method to make it something like this. It's not so bad, all right? The hexagon only contains 4 triangles, and most of them are well shaped. But if you want to crack it a little bit, you want to get a fraction along this line. All right, it divides this hexagon into 2 parts. But here it's not that good because once you divide you divide the hexagon using this line, you also need to re-triangulize it, adding more edges over here to make everything still be a triangle. Right. And so what about, okay, let's do it again. Let's add another line over here. And this one becomes a mess. So this is our example. We are adding 2 lines on this hexagon. It only divides the hexagon into 4 parts. All right. But if you start from a already triangulated mesh, you end up with this. So there are 2 things about this mesh being not good. The first one is there are too many triangles you are dealing with, and the other one is the triangulation of this one is kind of terrible because you can see there are lots of skinny triangles. If you want to do a future physics-based simulation on it, you see the rest shape matrix is almost singular, and you will cause lots of other problems. All right. So the basic idea of the prefactor method is to just work with those polygons. So think about this this division of the mesh. We can also define it using a Voronoi diagram. Okay, so if we define, let me see if I draw a circle over here. If we define 1, 2, 3, 4 vertices. So those vertices can be seen as a Voronoi center, and the entire mesh should be able to just divide. We can divide the entire mesh using the Voronoi diagram using those 4 vertices. All right. Let me elaborate it out a little bit more on what is the Voronoi diagram. Let's see a Voronoi diagram. Okay, so if I have a region, it can be bounded or unbounded to extend it to infinity. Let's say this is a bounded region here, okay? And the domain is x. And we can define an arbitrary distant function, dx1, x2 equals to, say, Euclidean distance, x1 minus x2 to norm. So this is a Euclidean distance between arbitrary 2 points in this domain. All right, and then I can put lots of Voronoi centers in this graph. The P1, like P2, P3, P4, and we can define a Voronoi region RK equals to x belongs to the domain such that the distance of x and the pk, which is the center of the region, is less or equal than xpj, where j not equals to k. Which means if a point is nearer to the center p3, like here, then it belongs to R3. All right, I can divide the entire region as something like this. And for so this is basically my Voronoi diagram, right? So one thing is it has lots of nice properties based on what kind of distant functions you're choosing. You can and definitely, if you're choosing different distance functions, they will result with a different Voronoi diagram. So, for example, if I have lots of vertices scattered over the space over here, this is when I'm choosing my distance as a Euclidean distance as the merit, and also I can also choose my distance as like a Manhattan distance, and you will result with different Voronoi diagrams. All right. So one nice thing about it, if you're choosing Euclidean distance as the distance measurement when you're calculating the Voronoi diagram, and the resulting shapes are always convexes. This is a very nice thing, and you can simply prove it because if arbitrary 2 points belongs to one region, then any point that interpolated between those two still belongs to this region. You can just prove it by using the definition of the Voronoi diagram. All right, okay, and this is but how are we gonna generate a Voronoi diagram? If you have only finite resolution, you can definitely go to like vertices by vertices to tell which one is the nearest the center of a vertex, and then just separate it using in this way. All right, or we can have a better cut using definition of Voronoi diagram. If I have a infinite space, still have P1, P2. P3 and also P4. We can generate this Voronoi diagram one vertex by one vertex. So assume we only have P1 in a space. So we know the entire space belongs to R1 because this is the only center that I can find. All right, and then I'm gonna procedurally adding new vertices into my graph. We can add a P2 into my graph, and then we can find a bisector between P1 and P2. So here it's still clear everything above this bisector belongs to P1, everything below the bisector belongs to P2. All right, and then we can keep adding it. Add P3. We can add a bisector between P1 and P3, add a bisector between P2 and P3. Here notice that those two bisectors must intersect with the first bisector at the same point, because we only have 3 points, and you can think of those 3 points as a triangle. And this point, what is this point? It's the center of the circumcircle of this triangle. All right, so they must intersect within 1 point. And also we can keep adding it, adding P4 to it. and find a bisector between P1 and P4, then P3 and P4, and P2 and P4. And the resulting Voronoi diagram looks like this way. So in that case, each point inside the region is nearest to those Voronoi centers, and we have a clean cut of this Voronoi diagram. And we call those joints Voronoi vertices, Voronoi nodes, and those P1, P2, P3, P4 like Voronoi centers. All right. It's actually you probably have already been using something like Voronoi diagram on your own, because it is really closely related to your favorite Delaunay triangulation. You've used it a lot, but if you use some third-party libraries to generate a triangular map to tessellate your mesh, like TetGen, and it's actually using this Delaunay triangulation. Right. So what is Delaunay triangulation? It's also something similar. If I have P1, P2, P3, and P4, I'm going to generate two triangles because there are 4 vertices, that I can minimize the maximum angle among all triangles. So this is the basic idea to avoid all the skinny triangles inside a mesh, all right? Because if I have 4 points, I can generate. There are 2 ways for me to generate those two triangles. And apparently, this angle, which is the largest angle among the entire mesh, should be smaller than this angle. And that's why this is a better way to generate your triangulation. This is called Delaunay triangulation. Okay, and there's another property which is equivalent to generating the minimum of the maximum angle of the entire mesh. It's saying that for every triangle, I can find its circumcircle. For this one, I can also find a circumcircle. And for all the circumcircle of one triangle, we want to make sure that there is no vertices on any other triangle that falls into my circle here. I can do it on this example. This example will have relatively larger circumcircles, something like this, and those 3 vertices will be even larger. Okay, so this is a counter example because in this case, like this vertex falls into the circumcircle of this triangle, while also this vertex is also falling into the circumcircle of this triangle. So this is not a valid Delaunay triangulation. All right. So there is a very interesting thing about this Delaunay triangulation versus your Voronoi diagram. They are mutually dual graphs. So the Voronoi diagram is a dual graph of the Delaunay triangulation. What is dual graph? So the centers becomes the nodes, and the nodes becomes the centers. And also, let me see, P3 and P4. So if we change those nodes to be centers, they are the Voronoi centers, and we change the centers of those circumcircles as nodes, those are the Voronoi nodes. All right. So that's why they're kind of mutually a dual graph. And once you have your Delaunay triangulation, you can come up with a Voronoi diagram and vice versa. All right. Okay. And how do we use this Voronoi diagrams when we want to simulate in fracture? because by looking at this one, it's this one is pretty nice. All right, think of it. This one is a piece of glass. If I drop it on the ground, it might just fracture into those small pieces, and each piece is it's guaranteed to be a convex, which is even nicer for my future simulation. All right, so the idea of using using Voronoi diagram to simulate fracture. It's just to say, if I have an object, I can place all those Voronoi centers in the way that I wanted, and generate a Voronoi diagram onto that. Use that as my fracture pattern. It's pre-fractured. It seems like the edges between all those polygons, the shared edges, are really fragile. Once I dropped it on ground, they will break into apart. It will break it apart. All right. And the problem is, how do I generate all those Voronoi centers inside this mesh? So for a pre-fracture pattern, the simplest way is to uniformly distribute it, uniformly and randomly distributed. Like the example that I have here. So under that circumstance, and once you can think of the material and dropping on the ground or something to be completely destroyed, then it will just shatter into small pieces. Okay, and also you can also distribute it to mimic the material properties. For example, if you have a wooden structure, if you have a wooden column, and once a wooden is getting fractured, it will go to those really small, thin, and long pieces to something like this because of the fiber inside the wood. Right? So in that case, you can just distribute your Voronoi centers and to be really skinny and long to something like this. They are really apart vertically, but close horizontally. So in that case, you will have those really thin and long Voronoi regions in your Voronoi map. And once you fracture that, it will go to those thin and long pieces that you want. Okay. Also, if you have a material which is very strong, like on two ends, but really fragile in the center, you can just distribute more vertices over here and the smaller vertices over there. So once you fracture that, this one, the center part will become really small, nice small pieces, where the two other the outer strong ends will remain almost the rest shape. Okay, and third one, which is I think this one is most interesting one, is if I have, since this is a piece of glass, and I'm shooting a bullet onto that. Okay, so you should be able to expecting that there will be something like the spider web shape, like, and there are really small fractures at the center of the spider web, but relatively larger pieces outside of it. Okay, so the reason why this is called a pre-fracture method is because we assume that we know where it will be hit. All right, if you're doing an animation, say if I shoot a bullet onto the window, then I know where the bullet will collide with the window. All right, so I need to know this part at the beginning of my simulation, not really simulation. And then I can distribute really dense Voronoi centers around my contact point and distribute sparser patterns outside of it. And if you're doing it in that way, once you generate the Voronoi diagram, you should be able to see those spider web-like shape. But that there is an assumption that you really need to know where it should be hit. All right, it's that.
Does it take a long time to calculate the Voronoi?
Yes. Yes. So that's why you do the pre-fracture on that, and so there are lots of cases like if you have a sphere, and it's a symmetrical on an arbitrary axis. All right, you know the sphere will hit something, but you don't know where it will be hit. It's okay because it's purely symmetrical. I can just assume this one is my contact point, and add lots of Voronoi centers around the contact point, and get it sparser and sparser on the real part. All right. So and then I'm gonna divide it into the Voronoi diagrams before my simulation. Once the sphere is hit over here, just to rotate it to make the contact point to my collision point, and then the sphere will be destroyed perfectly. All right. So that's why lots of like game technologies are using this kind of technology, because we can pre-fracturize it, and once in a simulation we can just use some ad hoc solutions to rotate the fracture pattern a little bit, to do some rigid body transformation to make it looks plausible. All right. Okay. So now, today, what I'm really mainly talking about is about this kind of technique. If I don't know what is the contact point, if you're playing a video game, you're shooting a bullet around, and we don't really know what are the contact points, and how do we do such kind of fracture, which has really nice spider web-like pattern, and doing it in real time. And this paper in SIGGRAPH 2013 called Real-Time Dynamic Fracture with the Volumetric Approximate to Convex Decomposition by Matthias Müller and colleagues are doing this. This is a pattern-based fracture, pattern-based. Fracture technique. So the key idea of this pattern-based thing is that when we want to generate a Voronoi diagram, this one's typically slow if you have lots of Voronoi centers to be generated. All right, but once you generated it, trying to find a convex intersection should be fairly fast. So the example is if I have a glass, a piece of glass, this is my window, and I have a pattern. This is my pattern, a spider web like fracturing pattern on that, and this one is pre-fractured. I know the Voronoi diagram of it, and but I don't know the hitting point. Say I'm gonna there will be a bullet over here. I'm just gonna move this pattern to align my contact point, to assume this one is the center of the pattern, and move the pattern onto that one, and trying to find the convex intersection, and try to clip my original convex polygon into small polygons. And there we go. Then we can find a really nice pattern on an arbitrary point. All right. Let's see. So this is the key idea of it, and I'm gonna illustrate how this paper is going to implement all this stuff. Okay. The first thing is my input shape. This shape is not necessarily really a convex to deal with, to start with. Okay, So I also have a cheat sheet for this. For example, my input shape can be a torus, which is definitely not a convex. But we can kind of decompose it into small convex pieces. It's very easy to do. So we call this input shape as a compound. They call the input shape as a compound. And the compound is made up of some small convex shapes, and we call those small convex shapes. Sometimes they're omitting the shapes just to call them convexes. All right. And there are three properties of those small convexes. The first one is a compound consists of those convex shapes. The second one is that all those convex shapes, all those convexes do not overlap. They share some edges, or in 3D they share all the faces, but they don't overlap with each other. And third one is all the convex shapes are connected together with each other by sharing a same face and opposite normal directions. All right, so they have opposite normal direction and sharing or partially sharing a face if and only if they're connected with each other. Okay, so this is my input compound. And also we have some fracture pattern like this one. We call this one a fracture pattern. The fracture pattern can be anything. It can be artistically designed or generated using Voronoi diagram. But one thing is, even if it's artistically designed, we want to make sure that each cell of this pattern needs to be a convex. So we can do a convex-convex intersection quickly. So on each part, it also consists of lots of convex cells. And to not make it ambiguous, they're calling it cells instead of convexes, because a compound is also made of convexes, and the pattern is made of cells. Sorry. It's made of cells. Okay. So now what we really want to do, this is my compound, and this is my my fracture pattern. So if I have an impact over here, and also we know this fracture pattern is centered at here, you just align those two impact places together. You can see it clearly, no problem. I have another one. There we go. Okay, we can just overlap with using our compound and using this fracture pattern. Okay, the first thing we want to do is overlap, is align. Try to align my compound with this one, with this pattern. And second one is we can, because all those convex shapes of a compound and all the cells of the fracture patterns are all convexes. And then we can do a convex-convex intersection test. After we have done the intersection test, we will split, or we'll clip all those convex shapes into smaller little convex shapes by using the cells. All right, so it is guaranteed that the intersection between two convexes are still convexes. So those smaller pieces are still convexes. All right. The third one is to weld. Because this one is originally a cell, we know the volume of the cell, or in 2D we know the area of the cell. All right. If a cell is really filled with convexes, we're just gonna group it back into one compound. And the fourth step is to group other compound that within one cell. For example, this one. Originally, it belongs to 2 cells, but we are going to group them. It belongs to 2 convexes. We're going to group them into one compound. It's okay. You can group something as if they are a non-convex shape. It's fine, because a compound can be a non-convex shape as long as all its components are convex shapes. All right. But this grouping has a little bit problem. Because if you see this one, this one, this one, this one, they belong to the same cell. All right. So we also need to do an island detection to make them to separate different compounds. And originally in the paper, island detection. In the paper, it was using a flooding algorithm. So they choose a convex to start with, and try to find all the neighbors which is connected to this one, and try to flood it until there is nowhere to flood. Right? And they do it once to see if it covers all those compounds. Until it sees if it covers all the convexes inside the cell. If it's not, they do the flooding algorithm again, starting from a uncovered convex. Do it again, and until every one of them has been covered, and then they can group the compound together, the convex together, into separate convexes, like this one and this one. And how to do this flooding algorithm? It also needs an operation to find the neighbors of all the convexes. You can also do convex collision detection. If they just contact with each other, you can think of them as they are connected with each other. But in the paper, it was doing a smarter way, because each convex are really polygons with several surfaces. They're polyhedrons in 3D with several surfaces. All right, and each surface, an arbitrary surface Fi can be represented as a normal direction dot product x plus a d vector. So this is a surface definition. We can sort it using the norm of the d vector to sort it into the 1D array. You can use your favorite sorting algorithm like a fast sorting, which takes n log n time. And then only compare all the surfaces with similar d values to see whether their normal directions are opposite, and if they are really opposite, then trying to see if they are overlapping with each other, at least partially each other. So if this detection is successful, then we can say that one convex is the neighbor of another convex. And they just do the sorting once, and they can find all the neighborhoods of all the compounds. All right. Okay. So the result of doing this one is to fracture the object completely. So once I have a has an impact location over here, then the torus will be separated completely. Like even this part will be apart, and like this, right? And also they did a small fix. If we only want a certain impact region to be fractured, so for each impact region, I can draw a sphere around the impact location. right? And everything that outside the sphere will be neglected. So they won't do the convex cell intersection test on this one because it's completely outside the circle. Sorry, outside the sphere. It's in 3D, and all the unaffected one will automatically be grouped together into one, and only those one which is inside the sphere or have partially intersection with the sphere will be applied on those steps. So they will do the split and weld them together, group them together, and do island detection. Oh, by the way, why there is a weld operation? Because it's so similar with the group. All right, they just group things together into one convex because there is an assumption each cell is guaranteed to be the convex. So if one cell is filled with all those components, we don't need to do island detection over here because it is guaranteed to be the convex. They must link together. They filled up the entire cell, so there's no island detection on the already welded ones. There's lots and lots of those small pieces, so it's really kind of an optimization step. So doing this step can make your code running faster. All right. And this one, done. So, and in this paper, it first come up with an algorithm to do a convex intersection and then split it into small pieces. And also it considered a partial fracture example by defining a sphere, a compact sphere near the compact location. All right, and also there is another property because our input mesh is usually not as simple as a simple torus or as simple as a piece of glass. It can be an arbitrary thing like a bunny. If we want to. Okay, so what if we want to fracture this one? Okay, so in this paper they call this one a visual mesh. It can be an arbitrary thing in this mesh. All right, and we have a bounding box out of it. This is a visual mesh. So what the paper did is the second part of the paper. This paper is called real-time dynamic fracture simulation using volumetric approximate convex decomposition. So this is a volumetric approximate convex decomposition, VACD. And what does VACD mean? At first, they want users to input the Voronoi centers to kind of separate the bunny into specific regions. So the user input is the Voronoi centers. Voronoi centers. Notice that if the number of the Voronoi centers is not so many, it's not so large, then we should be able to do the Voronoi diagram quickly. And we can provide the user using an interactive tool to let them select how many Voronoi centers they want and where are those Voronoi centers. Okay, and say the user only chooses 2 Voronoi centers, one here, and it will generate a Voronoi diagram using the user input. Okay, so those two steps are kind of iterative steps. So user can keep editing the Voronoi centers until they are satisfied with the current Voronoi diagram. And for example, in this paper, if you see this really complicated dragon model with 40K vertices, the user only needs to specify 12 Voronoi centers on that dragon, and they will generate a Voronoi diagram here. Okay, And then the third one is called mesh clipping. It's also simple because I have our original bounding box. And after we have separated into the Voronoi diagrams, we can separate the mesh using its own Voronoi region. So the bunny will be separated into two parts. Those are the ears. And also I have the head. Something like this, right? So after the mesh clipping, we can see that there is one mesh with two separate components. We don't want those both of the 2 ears flying together if there's an explosion below that, right? So the fourth thing is also doing island detection. And this time, doing island detection is much easier because we have the mesh information. If you have an OBJ file, all the connected faces are explicitly maintained inside this OBJ file. You should be able to see whether those two parts are connected together fairly easily by just go over the information on the OBJ, or whatever kind of mesh format. After we have done the mesh island detection, we should be able to separate all the islands into two different parts. And the fifth one is to do a convex fitting, because the original AABB, the axis aligned bounding box, seems not to be so well tight fitted. All right, because when we want to do the future simulation, we want all the bounding boxes to be tightly fitted, and actually we want to use those bounding boxes directly as our fracture tool. So how to do this convex fitting? Let me keep this bunny. Just to keep the face part. Okay, so ideally we want to find a bounding box, like a convex bounding box, like this way, which is tight enough to run the simulation. Right. So there are several techniques to do this one. So the simplest one is trying to move the bounding boxes using a certain direction until they hit something. So originally, we know the bounding box is fine. It's guaranteed to be a convex because it was originally computed using a Voronoi diagram, and we just want to shrink a little bit, but we still want to maintain it to be the convex. All right. So we can shrink the axis aligned bounding box to make it tighter. Or we can make more directions. So there is a generalized version of axis-aligned bounding boxes, which is called a discretized or oriented polytopes. So in 3D, an axis-aligned bounding box is just a polytope with 6 faces. Right, we can define more faces. So if we want to define our axis-aligned bounding box, it's basically 1, 0, 0, 0, 1, 0, 0, 0, 1 at the face normals, and it negates. So there are 6 faces. Or we can define something slightly more complicated. We can define the planes to be something like 1, 1, 1. Negative 1, 1, 1, 1. Sorry. Negative 1, 1, 1. 1, negative 1, 1, and 1, 1, negative 1. If we define the plane directions to be those 4 plane direction and its negates, it will end up with a polytope with 14 faces. It's a 14 dope bounding box. All right, we can do it even in a more complicated way, just to define it in more directions. And there are also widely used 26 dop bounding boxes to make it tighter. So the basic idea is just to make it tighter. So in this paper, it's using a slightly better example. So still I have the bunny. And I have all the vertices on the surface of this part. The first thing is you should be able to run a tightest convex hull generation on that bunny using something like n log n time, where n is the number of the vertices of the bunny. It's basically just one sort. You can sort it using the angles between an arbitrary point and the origin, sort it using the counterclockwise or clockwise direction, just to run the convex hull generation technique. But also there is an approximate convex hull generating technique, which is we are keeping adding new vertices into my convex. Say originally, say I have only 4 vertices, and this is my convex hull. All right, and then I can add a new vertex into that, and this becomes my new convex hull. And also adding one more, so my convex hull will become to something like this. And we can keep adding it, but not adding a lot of vertices, just adding randomly like 10 or 20 vertices inside. We should have an approximate convex hull of this object. And it should be run in a very fast way, but after running that, we should be able to get something like this. It is a convex, but it's not containing all the vertices inside. So we are using those the surfaces of those convex hulls as the plane directions to do the same technique as this shrinking technique. And we should be able to create a convex hull to something like this. And this one is claimed to be the tightest fit, just given a really small time budget. Okay, so after we have done this VACD, then we can separate an object with little pieces and their tightly fitted bounding boxes, and then there are also convex bounding boxes. And then we can run exactly that same technique over here. We're gonna, which direction is correct? Yeah, we're gonna align a fracture pattern onto that convex, that compound, and then fracture it using the techniques that I was talking before. All right. So there's one last detail. Is about if you have an artist who can create lots of 3D contents for you, it's not necessarily a watertight manifold that they give it to you. For example, if I want to create a building with 4 columns, okay, an ancient Greek building with 4 columns and a roof and a sail. Okay, this is usually what artists will give you. There are intersections between the roof and the ceiling, and also it's not a manifold. So if you get this mesh and simulate the simulate the fracture directly, you will detect the collision between the columns and the roofs at the beginning of the simulation, and just explode the roof violently. Right. So it's also something that is not ideal. One thing is we can simply fix it by telling the artist to please go back and redo it. No, it's not an ideal way to do that. The simple fix of this method of this thing in the paper is to introduce something called a ghost convex. So we are So in this paper, they are assuming all those little pieces are really convexes. So the intersection between those 2 pieces is still a convex. All right. If I have a convex intersect with another convex, I got a new one. And this one is defined as a ghost convex with negative volume. And in simulation, it's just treated as a normal convex, but they don't render it out. So in that case, when you want to do collision detection, this box is no longer collided with this one, because you will treat it as a contact with this negative convex. So while they are connected, the surface normal of this face is pointing upwards. The surface normal of this face, because it's all pointing inwards, it's something like this. All right, it matches a property that we are introducing our compounds. So remember, inside our compounds, if two convexes are connected, the only condition that to say they are connected is to say they have opposite normal direction and they share the same face. But it also happens here. It's just they're just two connected shapes instead of two shapes that intersect with each other. And also it happens on this shape and this upper left box too. And then you can just apply all the simulation routines and just simply don't render it out, render those ghost components. Okay, and that's how this method is working. I can also show you some demos of this paper. It will not be recorded. I'm gonna stop my record over here and show the demos of what I said in this class.